Hello students, welcome to the Fundamental Physics Lab. Today we're going to be looking into the Mech-08, aka the standing waves in the strings. This is part of the Fundamental Lab class offered by the Department of Physics and Material Science here in Chiang Mai University. So first of all, before finding a standing wave in a string, you should know some fundamental about the wave in the strings. So if you create some sort of wave in the string, the velocity of such wave is going to be given by square root of t divided by mu, where t is the tension and mu is the linear density. So to measure the linear density of a string, all you have to do is measuring the mass of the entire string and then divide it by the length of the entire string. So once you divide the mass by the length, you are gonna get mu in terms of kilogram per meter. And from there, if the string is being pulled by a tension T, in this case, if you hang a bob on the other side of the string and put the string onto the other end of the electric fork, here the tension is going to be determined by the mass bob that's being hung here. So the mass bob is going to be the tension force of mg that's pulling here. Okay. So once you turn on the electric fork, it's going to create a vibration along this direction, generating wave that propagates along this direction. And the speed of propagation of the wave is going to be determined by v equals square root t over mu. Therefore, if you increase the mass here, the mass bob, once the mass bob is increased, you can manipulate the tension, and by manipulating the tension, you can change the velocity of the string, the velocity of the wave in the string. And once you create a vibration at a given frequency, for example, in this case, if you create the frequency of 100 hertz of the electric fork from here, you fix the frequency of the propagating wave. However, by changing the velocity, you can change the wavelength of the propagating wave. Okay, so therefore, since v equals f lambda, with the more mass hanging on here, you can actually increase the lambda of the wavelength of the propagating wave by increasing the mass of the bob hit right here. All right. So the thing is, once you create a vibration, the wave is gonna travel from left to right. However, once it hit this boundary condition, this is a fixed n. Therefore, it would bounce the wave back. So you would have one wave propagating from the source from left to right, and another wave that's coming from right to left due to reflection. So by having the wave that has the exact same frequency and wavelength interfering one another, but traveling on different direction, aka the green wave coming from left to right represent the wave that's being generated from the electric fork, and the wave that comes from right to left is the wave that's being reflected from the pulley side, which is labeled as the blue wave right here. You can see that at certain point of the period, you can see here that if the total interference can be represented by the red curve right here, you can see that the red wave does not move. And apparently, you can also see that the red wave has a spot that is always destructively interfered between the green wave and the blue wave. So if the blue is pointing up, the green is going to be pointing down, and if the green is pointing up, the blue is going to be down. So consecutively, at this point, both of these waves are going to destructively interfere with one another, creating what you call a node, aka the point where nothing moves. And on the contrary, you can see that on this point, the vibration is amplified because the wave always interfere with one another constructively. So from here, you can see that the amplitude is increased because no matter the blue or the green are at a given time, they always have the same direction. So this is like a constructive interference, and then you would have destructive, constructive, destructive, constructive consecutively. So if you mark the destructive point, which is called the node, and the constructive inference point, which is called the antinode, the distance between the two nodes, you can tell from this marking that it's only half the wavelength. The full wavelength, you need to take two nodes. So so by measuring the distance between one node to another node, you get the information of the wavelength of a standing wave. Okay. However, not every single condition would create a standing wave. The standing wave is only satisfied when the lambda actually matches the boundary condition right here. For example, on the left side, the fork is giving the vibration, and on the right side is the pulley. So by having that, you can actually have this one antinode right here, and the fixed end on the left side and the right hand side is going to be always the node. So here you can tell that this is one node. This is one antinode. Therefore, the distance between the two nodes, is going to be half a lambda. Since you know that in this setup, L is fixed, so lambda is going to be twice the total distance here. However, once you increase once you increase the number of nodes right here, you can see that you can reduce the lambda, and the condition that the lambda has to satisfy in order to create this standing wave is that this whole lambda has to be the entire length here. Therefore, if I write it a little bit funnily, lambda is going to be 2L divided by L, aka lambda equals L. But I'm writing it this way so that you can see the pattern, because if you do the same thing by analyzing, okay, two nodes, one lambda, and you have one more extra antinode right here. Therefore, you can actually calculate the lambda to be 2L divided by 3 divided by 4 divided by 5. Therefore, you can generalize this equation to be lambda equals to L divided by N in order to satisfy this standing wave. And from there, you since you know that V equals F lambda, but you also know that for a wave in a string, V equals square root F divided by mu. Since I've already mentioned to you that F can be manipulated by changing the weight on the pulley side. So if you change F, you can change V. F is fixed here, the frequency is fixed. Therefore, if you put F right here is the tension, the force that's being pulled on the string. So therefore, if you make a plot, you can actually make a plot of force versus lambda squared. So if you put mu onto this side right here and then take the square on both sides, you can write down F equals mu F squared lambda squared. So here, if you change the force and you change the lambda, you can actually use the relation between the force that's being pulled on the entire system with the lambda square, which you can calculate using this formula. You can find the mu or the frequency of the wave that's inside here by using this relation. So if you make this plot, so once you plot the relationship between the force and the lambda squared, you can actually use the slope labeled in red here to do two things. On the first part, you're going to be given mu, so you need to find F. So once you know mu, you can actually calculate F from the slope, and vice versa. On the second part, you're going to be given an unknown mu, and then you already know F in this case. And by knowing F, you can actually calculate mu from this relation once you have plotted the relationship between F and lambda squared, and use the slope to calculate either mu or F on part 1 or part 2. All right? Okay, so please enjoy the lab. Thank you.